What's up? How are you doing?
Hey, I'm doing good. How are you?
I'm doing good.
So Sid, you're in your third year, right?
Yeah, I am. Yeah.
So are you like graduating next year or are you just graduating early?
I'm graduating this year actually. Yeah,
Oh,
next
okay.
semester. Hmm?
So I'm assuming like you're doing like a study abroad program or
No, I'm trying to do a post bac at the NIH. That's
Oh, wow.
yeah.
Okay. So is that like sorry, is that like another degree or is it just like a program?
It's just like a program, just like research. So it's like basically, I think you get like a $30,000 stipend, and basically you just work in a lab at the NIH for a year.
Neat, neat. So did you like already apply and
Yeah, so
yeah.
I submitted my application, but you have to reach out to labs and kind of like find a lab. So I'm kind of in the process of that right now.
Cool. Good luck.
Yeah. What's up, Rishal? How are you doing?
What's up, Seth? I'm good. How are you?
I'm doing good. Are any of you guys watching the World Cup?
Yeah, I've been watching it pretty closely. It's been really entertaining. So,
Yeah.
how about you?
Yeah, I've been watching. I watched the like both. I watched the USA Iran game and the USA Netherlands game. But those are the only games I've like watched in full. But I've watched like clips of the other ones. But yeah, I want Brazil to win though.
They were amazing today.
I
They were
know
like, yeah,
they were
they had
like
like,
they were destroying South Korea. That was crazy.
yeah.
Yeah. Yeah. What's up, Cam? How are you doing? I'm doing good. So wait, maybe like 2 more minutes and we'll get started. All right, so let me share my screen. All right. Awesome. So thanks everyone for coming today. So we're actually going to be doing a physics passage today. So this is a pretty important concept on the MCAT, like the idea of sound, Doppler effect. So today's passage is called Ultrasound and the Eye. So I don't think we really need an icebreaker today because I think everyone kind of already knows each other at this point. So here we have a wave. So can someone kind of explain the idea of frequency and amplitude of a wave?
Yeah,
Mm.
I can.
Yeah.
So amplitude is I believe the height from the trough or the lowest point to the tallest point of the wave, the crest.
Yeah.
And frequency is how often one period of a wave occurs, I think.
Yeah, exactly. Yeah, so frequency is kind of like how often one period occurs. And so if you have a shorter distance between the peaks, that means you're going to have a higher frequency because it takes less time for one period of a wave to pass through a certain point. So, okay, we have that. So does anyone know of the Doppler effect? Can anyone just explain it off the bat if you've already heard of it?
So,
Hmm.
it's like it only applies for sound sources that are moving. So like if it's moving towards you, like if an ambulance is moving towards you, then the waves get compressed because like it's releasing the waves at the same frequency, but because it's also moving towards you and the waves are also moving towards you, they like combine. So it makes it compressed and the higher frequency, which is why like the ambulance gets higher pitched as it comes towards you. And as it goes away from you, the opposite effect occurs. So
Yeah,
that's why it goes back down.
exactly. Yeah, so that's exactly so yeah, the Doppler effect is basically so every sound source emits the same the frequency of a sound source is always the same whether it's moving towards you or away from you, but the frequency that you hear, aka the observed frequency, depends on where the object is moving relative towards you. So the emitted frequency is always just one frequency, but the frequency that you observe as an observer differs. So like Andy explained, so if an object is moving towards you and you have a wave, so like think over here, since the object is moving towards you, each wave is going to take less time to hit you. So the wave is going to become more compressed. So it's going to become higher frequency because even though the emitted frequency is staying the same, because the object is moving towards you, it takes less time for the next the next peak to hit you. Does that make sense?
Yes.
Makes sense. So, and the same thing, if the object is moving away from you, for example, this car is moving away from this woman in this picture. So each peak is going to take longer to get to her because the car is moving away from her. So it's going to kind of like stretch out the distance between the peaks and make it lower frequency. Okay.
So it it only applies to like a moving sound source.
Yeah.
Okay.
Exactly.
Or what if someone was moving and the sound?
Yeah, that's also a really good point. If you're moving towards it, it's the same thing. So like even if the source is stationary, like for example, let's say that car wasn't moving, it was just there, but you were moving towards it, you would hear a higher frequency because it's taking less time for the next peak to hit you. The next peak of the wave. So these like waves are, these peaks are getting closer together. So it's a higher frequency.
That makes sense.
Yeah. So yeah, and then opposite, if let's say you were moving away, let's say, yeah, you were moving away from the car, then your frequency would decrease because the peaks kind of stretch out. All right. Let's see. Okay, so we explained Doppler effect. And so this is the formula used for Doppler effect. So let's look at it. So this F in the purple, the F in the purple is the actual frequency. This is the emitted frequency. So the frequency that's being released by the cop car, for example. The F prime is the frequency that you hear, like the frequency you observe. So VO is the velocity of the observer. So whenever you're moving towards the object, that's positive VO. And if the source is moving towards you, that's positive VS. Right? So let's say you have a positive VO, right? Your numerator is going to increase. That means your observed frequency is going to increase, right? And let's say you have positive VS. Because you're subtracting VS in the denominator, your denominator is going to get smaller and the overall fraction is going to get bigger. So you're going to have a higher observed frequency. Okay. So can someone explain how that formula kind of lets us know about Doppler effect?
Well, like with the velocity of the observer, if the object is moving towards you, it's going to be positive. So that means the numerator is going to be larger, and so that means the observed frequency is going to be positive or larger. And
Yeah.
with the velocity of the source, if it's positive
Mm.
or you're moving towards it, I guess, then that means it would be positive, and that would make the denominator smaller, so the observed frequency would be larger.
Yeah, exactly. So VO is the velocity of the observer. So yeah, so VO would be if you're moving towards the car, whereas VS would be if the car is moving towards you. So same thing, they're moving closer together, but VS means the car is moving towards you, and VO means you're moving towards the car.
Okay.
Yeah. Yeah, but yeah, that's right. Awesome. Okay, and now we use the Doppler effect in ultrasound. So ultrasound is when you use it in a medical setting, and basically you send a wave to a tissue in the body, and the wave bounces back towards you, right? But we can use Doppler effect to measure the velocity of, for example, blood flowing in our body, because the wave that comes back is going to experience a Doppler shift. Because the wave that's reflected back is the same thing as the wave that the blood vessel here receives. So because the blood is because, for example, here the blood is moving away from the detector, so your observed frequency would be smaller, because the wave going back is going to have a decreased frequency because it's going to be Doppler shifted. Let's see. Yeah. So does anyone have, I'm not sure if that was a good job of explaining Doppler ultrasound, but does anyone have any questions about that?
Can you re-explain it one more time?
Yeah. So basically, so you send a wave at the blood vessel, right? But that because the blood is moving away from the transducer, the thing that's sending the wave is going to be shifted. So it's going to experience a Doppler shift where the frequency is going to decrease. And so that wave that it sends back to the transducer is going to be a wave with a decreased frequency. And based on that Doppler shift, you can tell how fast this blood is moving, because if the blood is moving really fast, you're going to have if the blood is moving really fast, you're going to have a high Doppler shift, right? Because if it's moving really fast away from you, you know your frequency is going to be decreased. So you can use that Doppler shift to tell how fast the blood is moving.
Why does it come back slower, or slower if it's moving away from you?
So it doesn't come back slower. The frequency decreases, because remember here we said, so think about this one. So like the car is moving away from this woman here. So each peak is hitting her. It's taking a longer time to get to her. So the wave kind of like stretches out. So think of the cop car here as the blood. So the blood is moving away from the sound source. So the wave that is coming here is going to be decreased frequency. And so the wave going back is going to be decreased frequency as well, because the blood is moving away. So basically all you need to know is that if the blood is moving away from the transducer, the frequency of the wave that goes back to the transducer is going to be decreased. For example, though, if the blood was moving towards the transducer, the wave that goes back to the transducer is going to be increased frequency, because all it's doing is it's sending out a wave and then it's detecting the frequency of the wave that comes back. And the frequency of the wave that comes back depends on how fast the blood is moving and in which direction the blood is moving.
So does the blood like carry the sound almost?
So basically the sound just bounces off the blood.
Okay.
Yeah. So you send one sound in and then it bounces off and the sound comes back. And then you compare the sound that comes back to the sound that you sent out. And then you can tell how fast the blood is moving and what direction it's moving in.
So it makes sense to kind of think that for a split second, for however fast the blood is moving, that the sound wave is kind of elastic and it like kind of like sticks to it, but the thing is moving and then it like bounces off in like the same like short amount of time.
So one way I like to think of it is, so basically there's two parts of this. So one part is that this blood first receives the sound, right? Just like this lady here had to receive the sound. Like the car was emitting the sound and that this lady over here had to receive it. So let's just think about that for now. So we're thinking about that. So the blood here has to receive the sound from the transducer, right? Because the transducer is sending out sound, right?
Right.
So it has to receive that sound. So because the blood is moving away from the transducer, it's going to receive a sound with a lower frequency, right? Because we learned that if something's moving away from something else, it's going to experience lower frequency, right?
Yes.
So if it experiences lower frequency, it's that wave that it experiences, it sends the same wave back. So it just like, think of it as it just reflects off. So the wave it receives, it sends back.
Okay.
So because the blood is moving away from this like sound source, it experiences it observes a wave with decreased frequency, and then it sends back that wave of decreased frequency, because it's just reflecting off the blood. So a wave of decreased frequency hits the blood and reflects off back to the sensor transducer. Does anyone have any questions about that? Can someone try to explain it just to see if they got a good grasp on it?
I think I can try to explain my understanding of it. So if the blood's moving away from the transducer, then it's going to come back with a slower frequency, and vice versa. And I think the reason why is because if we can imagine the blood was just stationary, like not moving at all, the frequency would come back the exact same. But if it's moving away, then like the net sum of like all the blood vessels that are like reflecting the frequency are going to be further away from the like where they would be if they weren't moving at all, which is going to kind of lengthen the distance almost.
Yeah.
And then the same thing for the opposite way.
Yeah. That's good. Yeah. That's right. So but except when you say the wave is you want to say the frequency is lowered and not slower, because we always slow and fast talk about like velocity, not frequency. So you just want to say greater or lower.
All right, thank you.
No problem. Yeah, but yeah, that was a good job explaining it. Awesome. So I think we can move on to the next slide. So
I have a question.
oh yeah, sure.
How does ultrasound, it doesn't only interact with blood vessels, does it? Or is it
Yes.
just blood vessels that interacts with?
So this is actually one form of ultrasound. So this is called Doppler ultrasound. Whereas there's actually other forms of ultrasound as well. So I think they use different ultrasounds for different tissues, but if you want to measure the flow of something in the body, like the movement, you want to use Doppler ultrasound.
So is Doppler ultrasound only going to return back frequencies that are changing, I guess?
Yeah, if something's moving.
Like variable? Okay, yeah.
Yeah.
Okay.
So you want to think of Doppler ultrasound, at least on the MCAT, for like something that's moving within the body.
Do you know what kind of ultrasound they use for like babies?
I think it's just called normal ultrasound.
Okay.
Yeah. But if you see the word Doppler, you know they're trying to measure the movement of something.
Okay, thank you.
Yeah. Okay. Sorry about that. Okay, so the next concept we have to learn is called refraction. So basically, whenever you have a wave and it enters a new medium, it's basically the new medium affects how fast it can travel. So for example, in this picture here, you see we have water, right? And then we have air. So sound or light can only move so fast in water compared to air. So they have what's called an index of refraction. So index of refraction tells you how slow you can move. So water, so which medium do you think is sound going to move slower in, water or air?
Air.
Air. Well, so it would move faster in air actually. So you want to think that sound moves pretty fast in gases. So air is like gas, and oh wait. Sorry, wait, I might have messed it up.
I thought sound like moved the fastest in like those metal.
Yeah, yeah. So yeah, yeah. So yeah, it actually would be. Let me think about this for a second. Sine theta smaller. Sorry, let me search something out. Okay. Yeah, so if you have a greater index of refraction, then that means, I mean, this is talking about light though, so yeah, so okay, let's just assume we're talking about light. So when light moves from so light is going to move slower slower in water than air. So you can think of it like that. So because light is going to move faster in air, its index of refraction is smaller. Right. Yeah, it's index of refraction. Sorry, that's a bit confusing. So, okay, let me start over. So basically, let's just talk about light. So when let's say you have light and it's leaving water and it's entering air. So it's going to go to an angle called, you see this purple line right here? So that's called the normal. So light is going to come in at a certain angle to the normal. And once it moves to a new medium, depending on that medium's index of refraction, it's either going to bend away from the normal or bend towards the normal. So index of refraction tells you how fast light can move in a medium. So if you have a higher index of refraction, light moves slower in that medium. Okay, so now that we have that, so Snell's law gives you a formula for the angle from the normal and the index of refraction. So if let's say you have a smaller index of refraction, okay, let's say n2 is smaller, but it has to be equal to n1 sine theta, right? If you have, let's say n2, so n2 is smaller than n1, but this thing still has to be equal. What should sine theta 2? Should it be greater or should it be less than sine theta 1? If these two things are equal and n2 is greater than n1, I mean, n2 is lesser than n1, what should sine theta 2 be compared to sine theta 1?
Should be greater.
Yeah, exactly. It should be greater. So that's why this thing is further away from normal because n2 is smaller. Okay. So that's the idea of refraction. So actually, I don't think refraction happens. I think refraction can happen with sound, but I have to look deeper into that. But okay, so we talked about this. Okay, so why this is relevant is because when you have ultrasound, you want the waves to return back to the probe so you can sense the image that you're trying to create. You want to be able to sense the tissue, and the only way to do that is to have the waves come back to you. And for the waves to come back to you, you don't want them to go in a different direction. So index of refraction can alter the direction the waves bend. So let's say you have, let's say you're coming from air, right? And you're going to tissue. Your index of refraction, the tissue is going to be different. So it could bend away from the normal. And that can influence whether your wave comes back to the probe. Okay. And then another idea is that if the tissue absorbs the waves, then less of them can actually come back to the probe. Okay. And one thing you want to know is that the velocity of the incoming wave doesn't alter the reflection or refraction. So does anyone have any questions about that?
Will index of refraction always be given to, or is there a way that you have to calculate it or anything like that?
Usually it should be small. Like usually they should tell you what the index of refraction is.
Okay.
Yeah. Yeah. So that is that. Okay. And then so another important idea with sound is that the intensity of sound is inversely proportional to the square of the distance away from the sound. So if you are 2 times the distance away from a certain sound source, you will have what factor like of the how much less intensity would you have if you were 2 times the distance away?
One-fourth.
Yeah, you would have 1/4 intensity because so intensity I here is inversely proportional. So r squared is the denominator. So if you do 2 to the power of 2, you get 4 in the denominator. So that's why you have 1/4 the intensity. So that's something to keep in mind. So someone else, if you had 3 times the distance away, how much less intensity would you have?
1/9.
1/9, exactly. Yeah. Okay. And last slide of the PowerPoint. So basically, does anyone know what power is in terms of physics?
Yes.
Hmm.
It's work over
Mhm.
time.
Exactly. And so one way, so work is always just energy. And so energy, for example, if an object raises its temperature, that means it's gotten energy put into it. And so if you multiply the heat capacity, so the heat capacity is basically how much energy you need to raise an object by 1 degree. And so if you multiply the heat capacity by the temperature change, you can find out the heat that goes into an object, right? And so let's say I told you an object heated it up in certain, like, let's say 10 minutes. So let's say I told you that, let's see, 67. That an object with a heat capacity of 60 heated up 10 degrees in 1 minute. So let's see, I have a marker here. Let's say our C is 60. Our change in T is 10. Okay. What's our Q?
$600.
600. Okay. So that means we had 600 joules. So let's say this was Kelvin for the temperature. We had 600 joules put into the object, right? And let's say I told you that happened in 1 minute. Using SI units, what was the power? What was the power for that problem? If I told you the object got 600 joules put into it over 1 minute.
Is it 10 watts?
Exactly. Yeah. So it'd be 600 divided by 60. Yep. So that's the correct answer. So that's how we would solve it. Awesome. Anyone have any questions about that? Okay. Let's see. Does everyone understand Doppler ultrasound? If not, it's okay. We can go over it. We can go over it again. So yeah, so basically, if the blood is moving away from you, the wave that comes back to the sensor is going to be decreased frequency. If the blood is moving towards the transducer, the wave that comes back is going to be increased frequency. All right. So, and so when a wave hits a new medium, it can bend. So it can that bending is called refraction. So if a wave refracts, for example, when you like shine a wave or send a wave at a tissue for ultrasound, the wave can bend, and then so it will come back at a different angle, for example. And that can affect how well you see the image, because for ultrasound, remember, we want to get all the ways back to our sensor to get a good image of the tissue. Okay. So let's look at the passage now. Okay. Can someone read the first paragraph of this for me?
Yeah, I can read it.
Mm.
Ultrasound utilizes high-frequency acoustic waves outside the range of normal human hearing, 20 Hz to 20 kHz. One of its many applications is the resolution of very small structures. An ultrasound probe contains a piezoelectric quartz or ceramic crystal with a mass of about 125 grams that vibrationally changes in size and shape when some amount of voltage is applied, producing ultrasonic sound. The resultant waveforms have consistent amplitude and frequency. When ultrasound waves are incident on a medium, some of the waves are reflected back towards the probe. An ultrasound image is produced by analyzing the differences in the intensity of emitted and reflected waves. Higher quality images are produced when a greater proportion of the reflected waves are able to return to the ultrasound probe for analysis.
Awesome. And then if someone else could read the second paragraph.
Well, ultrasound with a 40 kilohertz wave can be used to measure blood flow velocity in the eye. The trajectory of the sound waveform can be modeled by Snell's law. The frequency shift of the ultrasound wave is calculated by finding the difference in frequency between the emitted and reflected sound wave.
Awesome. So here we kind of have the Doppler effect here. So if the object is moving towards you, the reflected wave is going to be higher frequency. So see this wave right here? It's waves, the peaks get smushed together in the reflected wave. So the reflected wave is higher frequency. Here though, if the object is moving away from the probe, the wave gets stretched out, the reflected wave. So that's what we talked about. And here it says equation 1 shows a version of the Doppler equation. So this Doppler equation lets you know about the Doppler shift for Doppler ultrasound. Okay. Awesome. Okay, let's try the questions now. Oops. Okay, could someone read question 1?
I can. A probe emits an ultrasonic wave towards an artery, striking the blood vessel such that the wave is traveling in exactly the same direction as blood flow. If the flow rate of blood increased, which of the following would be observed?
Awesome. So let's think about that. So let's say we have a blood vessel right here, and the blood is moving in this direction, right? It says the wave is parallel. It's exactly the same direction as the blood. So let's imagine we have our transducer right here, right? And we're sending this wave and it's traveling. That's such a bad wave. Okay. Eraser. Okay. It's sending the wave in the same direction as the blood. Okay. So which way is the blood moving from the transducer?
Away.
Away. And so how we can tell that is the wave is always going to move away from the transducer, right? The transducer can't send a wave back on itself, right? The wave is always going to go away from the transducer. So if the blood is moving in the same direction as the wave, that means both have to be moving away from the transducer, right? Because if you think of a transducer right here, it can only send waves away from it, right? It can send a wave this way, right? So for the blood to be moving in the same direction as the wave, both have to be moving away from the transducer. So if blood is moving away from the transducer, what's going to happen to the frequency of the reflected wave?
I think the frequency would decrease.
Exactly. And that is the correct answer. Awesome. Anyone have any questions about that?
So just to be clear, the incident wave is the wave being released from the transducer before reflection, correct?
Yes, exactly. Awesome. Okay. Question 2. The piezoelectric crystal increases in temperature by 0.7 Kelvin during a 5-minute ultrasound examination. What power was produced by the ultrasound probe in heating the crystal? Okay, so we can kind of think back of what is power? Can someone tell me the formula for power?
Power is equal to work over time.
Awesome. So how can we tell how much energy was transferred into the crystal? How can we tell what the work is?
It's the temperature change.
Exactly.
Well, C delta T.
Exactly. So Q equals C delta T. So what is C in this example?
116.
Exactly. And what's delta T?
0.7.
0.7. Yep. Awesome. And what is our time? It says
60 seconds. I mean, sorry, 5 minutes, not one.
So what is 5 minutes?
300 seconds.
Right. Okay, so we would get 116 divided by 300. Okay. Let's see. So what does that simplify to? So the weird thing on the MCAT is that you actually don't get any calculators, so you kind of have to do all the calculations in your head or by hand. So try to simplify this. 116. 16, 7 over 10. This should be a pretty easy way to do this. I think this should be, let's see, should be about like 77, 7.7 basically, approximately. So this is approximately, so you kind of want to just use approximations on the MCAT. So how I did that was I just thought of this. Oh, sorry, my bad. That was my mistake. That should be 77. Yeah, this should be 77, not 7.7. Let me erase this. Does anyone have an easier way for simplifying this?
I did. I was able to do 0.7 divided by 300, and I got 0.00233. And you could just do that times 100, like you suggested, and I got like 23.
23.
Sorry,
Yeah,
20.
that's pretty close to the
Yeah,
correct
yeah.
answer. This one. Let me see. Yeah, let me try that. Let's see. That would be 7 over 10. 1 over 300. That'd be 7. So it'd be like 116 over 300. Wait, what am I thinking? 116. Sorry.
It would be 1616 times 0.00233.
Right. But did you get that by hand?
Yeah, I did that by hand.
On that.
Because you could just do 7 divided by 300.
Yeah.
Just move it over 2 decimal places to get 0.007 divided by 3. 7 divided by 3 is like two and a third,
Mhm.
right?
Yeah.
And then just move it over.
Yeah. So yeah, so that would be, I'm just trying to think. Yeah, so you get 81.2 over 300 if you did, sorry. This math is actually kind of bad because they're not really going to give you this hard of a calculation on the MCAT. Or yeah, so what I did is I just divided 116 by 10, so I got 11.6. And then you get 81.2, and 81.2 is divided by 300. And that gives you about 27 over 100 because 3 goes into 81 27 times, and 3 goes into 300 100 times. So that's how I got. So hopefully it's good, Samir, that you got the right answer, but hopefully you shouldn't have to do a calculation that's that time consuming. Does anyone have any questions about that besides the calculation? No questions. All right. Awesome. Okay, can someone read question 3 for me?
Researchers performed ultrasound using a 40 kilohertz ultrasonic wave, which traveled through the vitreous humor of the eye at a speed of 1,532 meters per second until it was incident upon the retinal artery, striking the blood vessel in a direction parallel to blood flow. If the velocity of blood flow is measured to be 0.019 meters per second, which the following approximates the frequency shift of the reflected wave?
Okay, so what formula can we use to calculate the frequency shift for Doppler ultrasound?
Can we use the one they gave us?
Exactly, yeah. So they gave us this formula for a reason. So let's plug in some terms. So what is F? So it says F is the frequency of the ultrasound waves emitted from the transducer. So what is the frequency emitted by the transducer?
40 kilohertz, so it should be 40 times 1,000.
Exactly. So you can write 40 times 10 to the third. Okay. V is the blood flow velocity. What's the blood flow velocity?
0.019 meters per second.
Awesome. Okay, and then it says it's parallel to blood flow, right? So if it's parallel to blood flow, what does that mean? What's the angle between the blood flow and the wave?
Zero.
Zero.
0, exactly. So you just have 1 here. Cosine of 0 is always 1. So, and then you divide it all by c. What is c? C is the velocity of the sound wave. So what's the velocity of the sound wave?
Or 1,532.
Exactly. Okay, let's simplify this. So 0.019, that is about 0.02. Okay. Okay. You can kind of think of that as 2 times 10 to the negative second. So 2 times 10 to the negative second, that gives you 800. So you get 1600. Wait. Yeah, about 1600 over 1532. Right. Yeah, and that's approximately 1. So does anyone have any questions about that calculation? So basically what I did here was I converted 0.02 to 2 times 10 to the negative second. And 10 to the third times 10 to the negative second gives you 10. So you do 40 times 2 times 10. That gives you 800 times 2 is 1600. And then that's how I got 1600 here. 1600 divided by 1532 is it's close to 1. So that's how I got 1. Does anyone have any questions about that? Did everyone get the same answer?
I did.
Good. Awesome. Sounds good. Yeah, so it'll be 1 hertz. Okay, almost done.
I can read this
Okay.
one.
Yeah, sure.
Which factor would have the lowest impact on the quality of the image produced by the reflected sound wave?
Okay, does anyone have any idea what the answer could be?
Would it be the velocity?
Yeah, it would be that.
Because I think like regardless of what the velocity is, the ratio is gonna stay the same.
Yeah. Exactly. So it's really not the velocity that matters. It matters more about the medium it travels into. So the index of refraction of the body tissue matters because it can change the way the waves travels. Remember, it says here in the passage that higher quality images are produced when a greater proportion of the reflected waves are able to return, right? So if the waves are being bended by refraction, that can affect their ability to return back to the probe for the image to be built. And the angle of incidence, remember we talked about Snell's law, that also affects the refraction. So that's going to affect the image. And then if your tissue is absorbing a bunch of the waves, they're not going to be able to come back to the sensor, the ultrasound sensor. So your image is not going to be as good. So that's why the velocity of the wave is the correct answer. Any questions about that? Okay, last question. Can someone read this one?
I can read it. To calibrate a new ultrasonic probe, an emitter probe is placed in position 1, which emits a sound wave that is detected by a receive probe at a distance r from position 1, which measures an intensity of 4 times 10 to the negative 4th watts per meter squared. The receiver probe is placed in a second location at a distance 2r from position 1. What intensity would be measured by the receiver probe at this distance?
Awesome. Anyone have any idea?
Would it be B?
Exactly, B. And can you explain how you got that, Kershaw?
Yeah, so since the distance is 2r,
Hmm.
you know, the denominator, you're gonna have a factor of 4 since r is squared.
Mhm.
And then, so since the 4 is in the denominator, you're like essentially dividing by 4, the intensity by 4.
Yeah, that's correct. Awesome. Yeah. Let's see, that's correct. And that's the end of the passage. So does anyone have any questions about the passage, the PowerPoint, the questions? Any questions? All right. If no one has any questions, thank you everyone for coming today. There were a bit of hiccups, but I think it was pretty good overall. So yeah. Does anyone have any questions or?
No, sir. Thank you.
Yeah, no problem.
Sid.
Thanks,
Yeah.
Sid.
Thanks,
No
Sid.
problem.
Good.
All right. Have a good day.
Bye.
You too.
Bye.